So if you would recall, we've been talking about complex roots of complex numbers. Actually, we've been talking about complex roots of real numbers, and I was going to leave it at that, but this is just, I think this is just too cool to just pass up on. So I'm going to spend one more day. I'll see if I can limit myself to one more day. Talking about complex roots of complex numbers. This is partially because I like spending too much time on niche things because I think they're neat. Usually about this time, especially when we start talking about complex numbers, one of the things that you'll notice in your math classes is that the following question will come up quite a bit. When am I going to use or need or do this in my career as a fill in the blank? Or what careers would I be doing? What jobs would I have that would require this very strange, seemingly niche knowledge? Which most students, when math classes get weird, most students are not asking that question, what jobs have to do this, in just so far as like, oh, well, what jobs have to do this? It's like, oh, what jobs should I be avoiding so I don't have to think weird things like this? In my calculus class, I just talked about conditionally convergent series, and that's where I break their trust in how addition works. So, but the point is, usually it's when math gets weird that this question comes up. If I spent all of our time just adding numbers, or even just doing simple things like converting from degrees to radians, or finding the sine of 1/2, or the sine, solving the equation sine theta equals 1/2 in radians and degrees, then everybody would be cool with it. No one would be asking this question. When am I going to do this in my career as a future fill in the blank? It's only when things get really weird and we have to start questioning what we know that people start asking this question, which means when this question comes up, that's how I know it's working. Because this is the question that you throw as the first line of defense. It's your natural resistance to things that are challenging the things that you believe. You know what I mean? So when this question comes up, that's when I say, it's working. So anyway, what are we talking about? Kind of like those old Head and Shoulders commercials. It's tingling, and that's how you know it's working. So if you would recall, an nth root of a number, any number has n nth roots. So these are the things that we talked about. Any number has n nth roots. So a number has 4 fourth roots. So that is 2 square roots, 3 cube roots, 4 fourth roots, and so on, 5 fifth roots, and so on. Moreover, these roots could be complex. And complex nth roots. Any number has n complex nth roots. So it'll have 2 square roots, 3 cube roots, 4 fourth roots, and so on. And these roots will be evenly spaced around the complex plane. They're evenly spaced around the complex plane. That is, square roots are 180 degrees apart. Cube roots are 120 degrees apart. Because we're taking the 360 and just dividing it by the number of roots. So the 180 is going to be 360 divided by 2. The cube roots are 120 degrees apart because there's 3 of them. And that'll be 360 divided by 3. Fourth roots will be 90 degrees apart. That'll just be 360 divided by 4. And then fifth roots will be 72 degrees apart. Because we'll just take the 360 and divide by 5. The thing that I want to add today is we want to, whatever number we're finding the root of, that's like the radius of the circle. So if we want to find fourth roots of a number, the number itself is the radius. So when we say a number has a bunch of roots to it, that's the radius of the circle. So instead of a unit circle, we use this for the radius. So recall that we had 3 cube roots of 2. So the 3 cube, oh wait, no, it wasn't cube roots of 2. I had cube roots of 8 because I wanted one of them to be 2. This is not the radius. I was phrasing it differently. Never mind. Sorry. The 3 cube roots of 8, I was going to think of this one way, and then I decided to go with the way that I originally did this. So forget that radius business. The 3 cube roots of 8 are 2. And then the ones we found last time, 1 plus or minus I times the square root of 3. Numbers are going to start are going to be looking weird, but like I said, sometimes math gets weird. Make sure I have the right example. The 3 cube roots, negative 1 plus or minus I times the square root of 3. And these 3 complex numbers are 120 degrees apart. 2 is at theta equals 0. There are 3 complex zeros. These 3 complex zeros are 120 degrees apart, and they're all on a circle of radius 2. So let's draw a picture of that. And then what we want to do is twist this and rotate it to a different number. So let's draw a picture of where these zeros are. There it is. It's a little bit big. Just a little bit. Yeah, the radius is going to be the radius is actually going to be the length of any one, because we had cube roots, and the cube root of a real number will always have one real zero, and then the other two will be complex. But if we start with a complex number, it might be that all three are complex. So the radius is going to be the radius is going to just be the length of all these complex numbers, the magnitude, if we think of them in terms of vectors. So the three cube roots of 8 are 2, and then -1 plus or minus I times the square root of 3. So those three numbers, 2 is going to be here. So here's the one on the real axis. I forgot to put my axes in. At least I remember to use the graph side of the paper today. But I still called it paper. And it's more plastic. Complex roots of real numbers will come in pairs. Complex zeros of polynomials with real coefficients will always come in pairs. But if we take the complex zero of a complex number, they might all be complex. But that would mean we're looking at zeros of a complex coefficient polynomial, a polynomial with complex coefficients. So let's draw the 2 and then -1 plus or minus I times the square root of 3. So here, so this real one, oh, this is not the x and y axis. It's the real and imaginary axis. So this is the point 2 plus 0I. So its coordinates would be 2, 0, real, comma, imaginary. And then down here, I'll have -1 minus I times the square root of 3. So its coordinates would be -1, negative square root of 3. And then directly above that, we'll have -1 plus I times the square root of 3. So the big idea is that we have 3 complex zeros of 8. And we verified that last time because 2 to the third is 8. -1 plus I times the square root of 3 is also equal to 8. -1 minus I times the square root of 3 is equal to 8. So all these are cube roots of 8. And they are 120 degrees apart. Notice that if I take this point here at -1 and then positive square root of 3, I can just single one of these out. If I draw a right triangle around this point, so this point is at -1 plus the square root of 3. If I draw a right triangle around this point, so we can find the reference angle, the coordinates mean that in the x direction, or in the real direction, we have a length of 1, and in the imaginary direction, or the vertical direction, we have a positive square root of 3. And if we use the Pythagorean theorem to find the hypotenuse, then we'll find the hypotenuse is 2. So that 2 distance, this is a circle of radius 2, so it should be 2. So if we do 1 squared plus the square root of 3 squared, and then the square root of all that, with the Pythagorean theorem, we get 2, which is the hypotenuse. If we find the reference angle, if we look at this 1, 2, square root of 3 triangle, and we want to find this reference angle, theta r, we could use any one of the trig functions that makes us remember that this theta r is a 60-degree angle. So if I adjacent over hypotenuse, I would say that the cosine of the reference angle is adjacent over hypotenuse. And that tells us that theta r should be a 60-degree angle. Any questions? So if we've got a 60-degree angle in here, a 60-degree angle in here, that means we are 120 degrees apart. There's 120. Here's 120. Here are the two 60-degree reference angles that are making up a 120-degree angle. So what I want to do with this picture is figure out the 3 cube roots of not a complex 8, but what if I took one of these roots and I took this whole picture and just turned it 90 degrees. So this first one, I'm going to rotate the 2 plus 0i up onto the imaginary axis. So that's what I want to do now. I want to try rotating the 2 plus 0i up to the 0 plus 2i. I want to take this picture and rotate it just 90 degrees to the counterclockwise direction. Then we're going to use what we know about trigonometry to figure out what the other two are, because we'll know that they're 120 degrees apart. And then we're going to verify that those all, if we cube all those numbers, we get the same thing. So let's draw another circle. Circle here. So now I want to look at this number where we're at 0, 2. That's 0 plus 2i. So we know that there should be, if this is one of the cube roots, the other two cube roots should be 120 degrees apart. So let's figure out where these points are. And let's figure out what their cube should be. So if I take 0 plus 2i and cube it, so 0 plus 2i, if I raise that to the third power, well, fortunately for our heroes, one of the terms is 0, so I don't have to do all that much multiplying. I can just, 2i to the third power is 8i cubed. But I cubed is minus 1 times I, so I'll have negative 8i. So now what we want to do is figure out what these other 2 points are, and then cube them. And then make sure that they all multiply up to negative 8i. Forgot my words for a second there. Happens a lot. So if I'm going to use, I think I mislabeled something previously. We're fine. So if I start off at 90 degrees, if I start off at a 90-degree angle, and I add 120 degrees to it, so if I do 90 degrees plus another 120 degrees, that's going to put us at how much? 90 plus 120 is going to be, we're going to be at 210 degrees. So wait, why did I add 90 to the 120? Glad I'm recording all this. Never record while you're distracted. Or if you're going to be distracted, get a script. I need to know what this angle is in here, because I want to draw, I know this side, this length is 2. Someone needs to help me out with this reference angle in there. Where's that going to be? Because I need this side to be a 2. Clearly, I need help today. That side's going to be a 2. I'm going to have my x-axis here. I'm going to have some reference angle up in here. And I need to find some coordinates here. Because we're going for the same thing that we did way back in the day when we were just solving triangles. It's just oriented a little bit differently. So what's our theta r in there? Well, if I'm eating up 90 degrees, going from the positive imaginary axis to the negative, negative real axis, I'm using up 90 degrees here. So in this angle, we have 30 degrees. So it looks like theta r. I'm going to take the 120 and subtract the 90. And that leaves 30 behind to be up in this angle in here. So theta r is going to be 30. All right, so if this angle is 30 and I have a hypotenuse of 2, I know that if I want to find the adjacent side, we know that cosine of 30 is root 3 over 2. Did I have the wrong angle in the previous example? I did. So cosine of 30 is root 3 over 2. Sine of 30 is a half, so cosine of 30 is root 3 over 2. And so that means the adjacent side is a root 3 and the hypotenuse is a 2. So the Pythagorean theorem, if we have a square root of 3 as one side, if we solve for the opposite side, we have the square root of 2 squared minus the square root of 3 squared. 2 squared is 4 minus the square root of 3 squared is 3. So the square root of 1 is 1. So our point down here is going to have a real coordinate of square root of 3. Oh, sorry, negative square root of 3. And a complex coordinate of negative 1. So the coordinates are negative root 3, negative 1. So the question is, if I cube this, will I still get the same thing, negative 8i? So let's cube that. So we need to cube a binomial. So we're just going to start off with squaring the binomial and then multiply by the third one. So negative root 3 times a negative root 3 is going to be a positive 3. And then we'll have plus I times the square root of 3. And then we'll have a plus another I root 3. And then minus times minus is a plus I squared. We still got to multiply by negative root 3 minus I, but we should simplify the square first. So I have a plus 3, and I squared is negative 1. So here's a negative 1. So a plus 3 and a minus 1 is going to be 2. And then I have like terms. So I have a plus I root 3 plus another I root 3. So let's multiply these out and see what happens. So I got 2 times the negative square root of 3 So I'll have minus 2 times the square root of 3. 2 times a minus I is minus 2i. And then 2i times the square root of 3 times the negative square root of 3 is a minus 2i times the square root of 3 squared, which is just 3. Minus 2i times 3. And then a minus 2i, plus 2i root 3 times a minus I is going to be minus minus 2i squared times the square root of 3. Now we want to simplify again. We have like terms here. We've got a minus 2i, and then minus 6i. So if I simplify, this term here is minus 6i. And I can combine the minus 6i and the minus 2i. That'll give us negative 8i. And also I squared is negative 1 still. So this term is actually plus 2 times the square root of 3. So now my 4 terms, now that we've simplified things, I've got a negative 2 root 3 minus 2i. The negative 2 root 3 and the plus 2 root 3 cancel out. And the negative 2i minus 6i, this gives us negative 8i. And that's what we expected. Because we looked at, this should be also a cube root, the cube root of the same number that 2i is the cube root of. So we're looking at the 3 cube roots of negative 8i. So we need to go in the other direction. And I did cheat a little bit by putting the 2i starting with a cube root that's on the imaginary axis. So really we're just rotating this 90 degrees from what we had before. But this, we can get a copy on, we just get a copy on the other side. This theta r is the same theta r that we had before. That's the same reference angle. So on the other side, we'll have just a mirror image of the previous triangle. With its hypotenuse of 2, and the theta r still in here is still 30. Because I've still got 90 degrees from the imaginary to the positive real axis, and then 30 degrees to make up the real axis to the hypotenuse, or the complex 0 that we're looking for. So with theta r still 30, the adjacent side is still square root of 3. And the opposite side is still 1. Any questions? All right. So we'll still get the same, we'll get negative root 3, we'll get a positive root 3 and a minus 1 times I. So that'll be the third of our zeros. Positive root 3 minus 1 times I, or coordinates negative root 3, positive root 3, negative 1. And we would want to verify that this this complex number, that when we cube it, we still get negative 8i. So we would still have to verify that the square root of 3 minus I when we cube it is also negative 8i. Any questions? All right. So the next thing that what we would want to do at this point is just play with this idea. What if one of the cube roots, if we were looking at a circle, oh, so the reason that we're saying that all three of these numbers, we're trying to figure, starting off with a 2i, what if I take the three roots that we had before of 8, three cube roots of 8, and I rotate one of those roots up to the imaginary axis? I want to apply the things that we know. We're still looking for three evenly spaced roots. If one of them is 2i, where are the other two going to be? So these three numbers should all be cube roots of the same complex number. And so the three cube roots of negative 8i are 2i, negative root 3 minus I, and root 3 minus I. So those are the three cube roots of negative 8i. And we just want to verify that cube roots should be 120 degrees apart. So I said, here, let's start with this one and find where these other two are, and then verify that these other two are indeed cube roots of negative 8i. So if we start off with a cube root that's of a number that's off at some angle, the other two should still be 120 degrees apart, because that's how cube roots distribute themselves. So if we just take any point on this circle of radius 2, take any of the points on the circle of radius 2, find out what the other 2 points are. They should all have the same cube. Now we can just take this and rotate it around. And that's what we did. We just started off with 2 and then negative 1 plus and minus square root of 3i, and then we rotated that 90 degrees to get 2i, and then minus root 3 minus I, and plus root 3 minus I. Still 3 points 120 degrees apart, still all cube roots of 8i. All right. So these would be solutions to a polynomial equation with complex coefficients. We know that the solutions, the equation is going to have complex coefficients because a cubic polynomial with real coefficients will always have at least one real zero. And here we have three complex zeros. So what we're solving is x cubed equals negative 8i, which would be the polynomial x cubed plus 8i equals 0. So there'll be three solutions to the x cubed equals 8i, and there'll be three zeros to polynomial x cubed plus 8i. And x cubed equals negative 8i is the same polynomial that you wrote. So, or x cubed plus 8i equals 0. Roots of numbers, solutions of polynomial equations, zeros of polynomials. Any questions? We went way over time. Sorry about that. We went over time because I confused myself and that slowed down the processor. So it's like when you have an old computer and you're trying to run too many things on it, then every single program you're trying to run slows down. And sometimes you could watch that happen in real time when your professor is trying to think about 4 different things at once. Actually, it was only 3 different things at once. And that was enough to just like kill my processing power. I don't have a lot of it left. So sorry about going over time. Sorry about sounding so confused. I only sounded confused because I was confusing myself for some reason. All right, that's going to do it for today. I will see y'all again on Wednesday. Everybody have a good couple of days, and thanks for playing.